If now, let's start today's lecture content. So this is going to be, if we finish the content today, it'll be the last lecture on partial differential equations. And we are going to cover the Fourier stability analysis, just a quick introduction to Fourier stability analysis, and then discuss how do we generalize the finite difference, finite volume, finite element methods we studied into 2 dimensions and 3 dimensions, and which is something you probably will see a lot in applications. All right. So first of all, we are going to continue our Fourier stability analysis. So we'll start with the equations. The derivative of u to t plus a advection speed, the du dx, is equal to kappa times d squared u dx squared. And from our last lecture, we are going to be looking at a periodic boundary condition. So u0 is equal to u at 2 pi. Okay, so that allows us to plug in a sinusoidal function, or what's called a Fourier series. So u, again, let me write clearly, u is a function of x and t. It is represented as a summation of different Fourier modes, where k is called the weight number, right? So the weight number goes from minus infinity to infinity in a complex Fourier expansion. So the reason it's called complex is because this u hat is now a complex number. So u hat k. So we have u hat of 0, subscript 0, u hat subscript -1, u hat subscript +1, u hat script -2, etc., etc. So these coefficients are purely function of time, right? It is multiplied with the exponential functions, or complex exponential functions, actually, I times k times x. So note that there is a little bit of a similarity between what we are doing here and the kind of finite element representation we did in the last lecture, using basically representing our solution as a linear combination of basis function, where the basis functions are just the functions of space. In that case, is a bunch of hat functions. And then the coefficients are purely function of time. This is similar, right? Except for the basis functions here are no longer the hat functions. Instead, they are basically periodic functions e to the ikx. So e to the ikx is a bunch of functions that are like that. So let's say this is x, this is 0, this is 2 pi. Okay, so let me first draw e of ix. So that's when k is equal to 1. So let me actually say this is e to the ikx. Okay, so first of all, what would the function be when k is equal to 0? Well, when k is equal to 0, we have e to the 0, right? Always. So the function is equal to 1. The 0th term is a constant. Okay, so that value here is 1. So this is k equal to 0. How about k equal to 1? So when k equal to 1, we have both the real parts and imaginary part. So let's just illustrate the real part for now. So the real part of k equal to 1 is a cosine function. So it's a function that goes like that, right? So this is for k equal to 1. Well, actually, if you look at the real parts, this is k equal to plus or minus 1. So let's just denote this as the real part of e to the ikx. Okay. All right. So that is for k equal to plus minus 1. When k is equal to plus minus 2, we have a higher frequency over here. sorry. So this has to be back drawing. So this is the period for the e to the I2x. So I have one period over here and another period over here. So that is my k equal to plus minus 2. All right. And we can go from here. So when k is equal to plus minus 3, I have to divide the domain into 3 equal parts. And I have a sinusoidal function in each of these 3 parts. So that is k equal to plus minus 3, etc. So that's the real component. And if you look at the imaginary component, that's the, instead of the cosine functions, that's the sine functions. And in order for the final answer to be real, right, then my u hat of plus 1 and u hat of minus 1, they have to be basically complex conjugate of each other in order for the resulting summation, resulting linear combination to be real. So, okay, so when k is equal to 0, we have 0, right? So when k is equal to 0, we have 0. So basically, k equal to 0 doesn't really contribute to the imaginary part. And when k is equal to 1, we have this. So that's k equal to 1. And the k equal to minus 1, we have the opposite, right? And the rest is actually has a one-to-one correspondence with the cosine term. So when k is equal to 2, I have, when k is equal to positive 2, I have the sine wave like that. And when k is equal to negative 2, I have the sine wave like that, right? So this is k equal to 2 and k equal to minus 2, etc. When I go to higher frequencies, I have the pairs going together like that. So this is basically a complex representation of a Fourier series. And the advantage is that when we differentiate the Fourier series du dx, as we have started working last lecture, we have a ik multiplied on u hat of k, still just a function of t, times the same basis function, the same Fourier basis, e to the ikx. Okay, and when we take a second derivative, it is equal to a summation over k. Now I squared becomes minus 1, so minus k squared u hat of k as a function of t e to the ikx. Okay, now what's interesting is when we plug in these 3 terms back into the differential equation. All right. Oh, 1 second. We still haven't looked at the time term yet. So the time term actually is easier to deal with than all the other terms, because when you look at this decomposition, the u hat is a function of time, while e to the ikx is not a function of time. Therefore, when you differentiate the whole thing with respect to time, we get ordinary derivative because u hat of k is just a function of time. Du hat dt times exactly, again, the same basis function, e to the ikx. All right, so now it's time to plug in these 3 into the original differential equation.